All right, welcome to Chapter 7, Data, Voice, and Video Cabling, 3rd edition, Network Cabling. What's my goal here? My goal is to hope that you will understand the installation and performance concerns for many different types of network transmission media. So unlike telephone and video cabling, which have used one basic type of cabling all along, computer networks have used many different types of cable and, in fact, several other means of communication. And all these methods have been tried as solutions to providing low-cost, high-performance cabling. And they include unshielded twisted pair, shielded twisted pair cabling, coax cabling, optical fiber cables, radio signals, infrared, electronic signals that are sent through power lines. Now, although most network cabling has migrated to UTP cabling following the structured cabling guidelines of the EIA 568, there are still applications that use other cabling schemes, and therefore a review of the entire spectrum of cabling will be needed to understand network cabling. Now, some of the cabling requirements that we need to talk about, okay, are with power work, and then we are most concerned about the path that the current is going to take, and less concerned about the quality of the power. And that's how electricity gets from point A to point B. Now, in data wiring, however, we have to consider two qualities of the transmission. First, we have to have a clear path from one machine to the next. And here we're concerned about the signal strength. It must arrive at the far end of the line with enough strength to make it useful, to make it readable. Second, we are concerned with the quality of the signal. So for instance, if we send a square wave digital signal into one end of the cable, we want to have a good square wave signal coming out at the other end. If the signal is distorted, then it's considered to be unusable. Even if it was still strong. So it's not just the strength of the signal, it's going to be the quality of the signal itself. First thing we want to discuss is something that we call attenuation. Now, attenuation, as I've said numerous times in a lot of my lessons, is the weakening of a signal over time and distance. Okay, that's attenuation. So basically, it starts off as a strong square and ends up as a weak square by the time we get to the end. Another thing that we want to discuss is called impedance. Okay, now impedance is really it's the opposition to the flow of the electricity or the data. It's important. It's an important consideration for coax and twisted pair cables. And the most important consideration for impedance is that it remain consistent throughout the entire data system. Next will be capacitance. As mentioned, capacitance is the most common element of attenuation. This capacitance between the conductors within the cable. Capacitance is a big factor because it causes the cable to filter out high frequency signals. Data transmissions are square wave signals, and when the capacitance is too great, it has a tendency to round off that digital signal. When data signals have a clear square wave, they're easily intelligible to the receiver. If, however, the signals become rounded, then they're confusing to the receiver, causing what we call a high bit error rate, or causing the data to be received in error, and therefore we just discard the whole signal. The next thing we want to discuss will be something we call crosstalk. Now, crosstalk is the amount of signal that is picked up by a quiet conductor from another conductor. Now, the signal is picked up through electromagnetic induction. So, in essence, when electricity goes down a cable, it creates what's called an electromagnetic field. The electromagnetic field on cable A is then going to be destroying the data on cable B, and the electromagnetic field on cable B is going to destroy the data on cable A. That's just kind of the easiest way for me to tell you basically how or what's happening with crosstalk. Now, there are ways that we can prevent the crosstalk from happening, and one of those would be shielding. Okay, now the shielding is just like an insulator. Now, there's different types of shielding. One is like an applied metallic tape, okay, almost like an aluminum foil, which essentially has to be grounded. And what that does is it acts as an antenna, absorbs the electromagnetic field, and then sends it to the Earth's ground where it needs to be. Another, which we use on coax cables, will be a braided shield, which is like metal, which is around the whole entire wire or cable. Typically, it's around the PVC conductor that goes around it, and that is then grounded, and then the electromagnetic interference is sent there. The foil laminated to a plastic sheet. Also, spirally applied metallic tapes can be used. Shielding stops the interference and crosstalk by absorbing the magnetic fields, plain and simple. The different types of cabling that we have. Now, our unshielded twisted pair and our shielded twisted pair are essentially the same, except for the fact that shielded would have a So, back to coax cable here. The thin net cable has a maximum distance of 185 meters. Thick net had a maximum distance of 500 meters. They ran in a bus topology, which is not compatible with today's networks. Today we go in a star topology. The former network did only a bus and was susceptible to more collisions. The other type of cabling we want to discuss is optical fiber cables. Now, here we use it for your FIDI and your fiber channel and your SCON. All versions of Ethernet can use fiber optic. The beauty of fiber, okay, high-end performance, excellent bandwidth in the high gigabit ranges, very long lifespan, high-end security, allows for very high rates of data transmission, causes no interference, and is not subject to electromagnetic interference. Disadvantages: a little bit higher in cost to install today, much higher than twisted pair cabling, but it would be the cable of choice in most of our networks today. You're going to find in a lot of your connections today we have a wireless transmission. So it seems weird that we're talking about wireless transmission when we're talking about video cabling itself, or I'm sorry, not video cabling, but for wired cabling. But you still have to get a wire into the wireless access point in order to send your data transmissions out. So, in the past several years, there has been a good deal of interest in wireless networks, although part of the reason for this interest is due to the expense of installing all the cables. The installation expenses are usually far higher than the material expenses and the frequent moving of terminals within a large office. And the most compelling reason is then you have to move the terminals from desk to desk. So put a wireless network card in, and then we kind of like don't have to have that issue. Now, some of the problems that we do have with wireless is the standards are always changing. The bandwidth is not as high, and the security definitely isn't nearly as high. And then there's also the supposed health potentials with radio emissions. You're going to find some people will be sitting there telling you that they're, oh, I'm going to get cancer because of wireless. There is no definitive study that's been completed that have indicated that radio waves in these frequency ranges of 2.4 and 5 gigahertz are harmful. And we'll talk about that a little bit more in the next chapter, chapter 8. Next we wanted to talk about is infrared transmission, which is a wireless transmission, uses pulses of infrared light. Give you an example of that would be your television remote. Okay, uses the same pulse pattern as cable pulses, requires the same parts. It is invisible to the eye. It is inexpensive, and it's limited to about 80 feet. Right. and is typically line of sight. Yes, you can bounce it off of a mirror or a window, um, and it's actually vulnerable to storms. The power line carrier network transmission is one of the ones that I personally find to be one of the most interesting, and I have a hard time understanding why it is not used more often, and we're all stuck with using Verizon and our local cable providers. Okay? So another method of sending data signals involves sending them through regular power lines. This method requires a special network adapter, modulates the computer data, and transmits it over the power lines in an office or a home. Now, other devices or computers connected in the same way may receive data over the power lines. The system is very attractive from the standpoint of installation costs, and no cables are required, and installation obviously will be very quick and easy. The system imposes data signals right over the power line current, and the voltage and frequency differences are easily separated from each other by a tuned receiver. The power lines operate at 60 cycles per second and 120 volts, whereas data signals are normally in the 5-volt range and have a frequency of hundreds of thousands of millions or millions of cycles per second. Now, power line carrier systems will never meet the technical performance of optical fiber cables or even other types of cables. They are, however, a very appealing option for home networks. So, for example, where computers in the future may control heating and air conditioning systems, turn lights on and off, and manage security systems. The installation of these systems is not completely hassle-free, however. Power lines do not travel unbroken throughout whole buildings or even through parts of buildings. So to bridge these gaps in wiring systems, special devices called signal bridges would then be required. And these devices connect to two separate wiring systems and transfer data signals from one to another without allowing current to be transferred with one system to another, which would then cause major problems and most likely cause injuries. Signal amplifiers are also frequently required when wiring systems cover long distances. There can also be filters and other devices required for these systems, depending on the locations and the installations. Okay? Now, other transmission means that we've discussed are, and by far the most common methods, or the ones that we've discussed by far, but there are methods that are sometimes used, and the chief among these would be microwave or laser signal transmissions for line-of-sight connections between nearby buildings. The typical method is to set up a transmitter and receivers on roofs of both buildings and then connect both ends to the networks in the buildings. The buildings can then be up to about a kilometer apart for most systems and even further apart for others. Signal transmission rates for these are typically around 1.5 meg per second or greater. Greater would not be as common. It is important to remember that in planning such a system, the management of any buildings and other or anything under the transmission area should be notified, and that any appropriate permissions are granted before any work will be done by your local municipalities, basically more so by the FCC when you're putting transmissions out over the airwaves in a public area. Which brings us into codes. And the NEC, Article 725, covers a Class 1, 2, 3, or 4 for remote control signal and power limited circuits. The article can be very confusing, so if you don't understand that the circuits designated for Class 1, 2, 3, or 4, what you need to understand is these are power limited circuits, or what we call signaling circuits. Every circuit covered in 1, 2, 3, or 4, some of them are power limited and some of them are signaling circuits. So what the heck is a Class 1? What's a Class 2? What's a Class 3? Okay. Class 1 circuits are supplied by a source that has an output of no more than 30 volts, okay, AC or DC, and up to 1,000 volts of amps, or volt amps, is essentially the same as the watts. Class 2 circuits are inherently limited in capacity. They may have no overcurrent protection, or they have their capacity regulated by a combination of overcurrent protection and power source. Class 3 circuits are similar to Class 2. They are inherently limited in capacity. They may require no overcurrent protection or may have their capacity regulated by some combination. Um, Class 4 circuits are Class 1 circuits that are also isolated, and they are used only for process control instrumentation. Power limited refers to a circuit that has a self-limited power level. That is, whether because of impedance, overcurrent protection, or other power source limitations, these circuits can only operate up to a limited level of power. Remote control and signaling circuits are the class 1, 2, 3, and 4 circuits that do not have a limited power rating. If we're going to take a look at the network cable handling, okay, the performance of the cabling network is heavily dependent on the installation itself. The Category 5E or 6 components used in most structured cabling installation systems today have been carefully designed and tested to meet or exceed the requirements of the TIA 568 for performance at 100 and 200 megahertz. You'll find most of your Cat 6 today is 500 or higher. If the cable is not properly installed, performance will be degraded. Also remember, you cannot mix components. Every component in the cable plant must be rated in the same category. If I have Cat 5e components in my Cat 6 system, the entire system essentially becomes Cat 5e. General guidelines when you're doing your installation: all components must be similarly rated for performance. Cable must be pulled from the reel or box without kinking. Cable must be pulled with less than 25 pounds of tension. Use cable lubricant if conduit is necessary. Cable must not be pulled around sharp corners or kinks. Inspect the cable routes for surfaces that may abrade the cable, which means that may scratch or cause damage to the cable. On riser installations, try not to lower the cable down, or try to lower the cable down. Don't pull it up. In case you're wondering why, when we pull, we end up with more weight on the bottom. As we pull harder and harder on the cable, it takes the twists out of the wire, which then degrades the wire's capabilities. Cables must be supported to prevent stress. Cable supports should not have sharp edges that may distort the cable. Cable ties must not be so tight as to distort the jacket of the cable. They are only used to prevent unnecessary movement of the cable. So snug is tight enough. The typical installation of communication cabling is in an office building. There are communications wiring closets on every floor and several if the floor covers a large area. A main communication closet will have the primary communications equipment, the PBX, the network routers, and so on. Cables will run from the wiring closet to the work areas overhead above a suspended ceiling, not on the ceiling tiles. Wiring closets will be connected by multiple cables run overhead or in risers. So as we look over here on the first graphic that we have on the left, each work area will be connected to the closet with at least 2 cables, one for telephone, one for data. Now, although the telephone cable can be Cat 3, it is more common today to install 2 Cat 5e cables or 6 for simplicity and easier cabling management. If the telephone company is already installed and only a data cable is being installed, only 1 cable may be needed. Okay? In the figure next to that, okay, cables are terminated in 8-pin modular jacks at the outlet and either in patch panels or in punch-down blocks in the closet. Closets may have numerous cables running between them unless the backbone cable is fiber optic, which will be only 1 cable with several fibers. Numerous cables will be needed to connect wiring closets to the equipment room. Terminations may be either punch-down or patch panels, or both depending on the destination of the cables. Some applications will have cables in conduit to protect cables in areas where damage may be possible, to prevent EMI where that might be the problem, or to assist in fire stopping. Remember, any cable that goes through a floor has to have fiber stop put onto it to stop the hole to keep fire from going from floor to floor. When we're pulling our cables, okay, especially with horizontal pulls, a typical installation, the cable will be pulled between the wiring closet and the work area above a suspended ceiling. This pull will involve routing the cables around everything else already there, including other cables, heating, ventilating, air conditioning, those systems, light fixtures, so on. So it's usually easier to do in new construction. And because the tiles are not in place and our racks are just hanging there, it makes the installation of our cables much easier. The most efficient way to pull cables is to use pull handles. Okay? Using drawings of the area, determine where all the work areas are located, and establish several consolidation points or clusters from which you may want to pull. This is easy with open areas and modular furniture, but may be more difficult in walled offices. Sometimes the best way to pull cables is from the work area, sometimes called the drop, and then take that all the way to the closet. And sometimes it's easier to go the other direction. The first step, however, is to gain access to the area. Clear as many obstacles as possible and then secure the area. Put caution tape around the ladder that you're working on and keep everyone away for safety, theirs as well as yours. And in the path you will be taking with the pull, carefully remove every other ceiling tile along the route, but leave them above the ceiling to prevent damage because you don't want somebody bumping into them in the hallway and breaking them. After checking out the area and finding the most direct route, tie a weight to the hand line or a pull string, typically a nylon rope, and then starting at one end, toss it from end to end. So basically what we're doing here is we're going to start at one end, we're going to take a pull string, throw it all the way down from point A to point B, tie that to our cables, and then gently feed our wires. We also then, when we get to the other end, we want to mark both ends of our cable. So we know that cable 1 is going to the location of cable 1 in the closet. So we have cable 1 in the work area goes to port 1 in the closet. Cable 2 in the work area goes to cable 2 in the closet. Okay? Put all of our cables together and then try to pull them all at once if you can. That is the most efficient way to do it. Okay? Run a hand line between the bundles and tie then your hand line to your tape, and then you're off to go. You're off and running. Okay. Here's one way that some people do it. I personally like the loop method. Now remember, just because you have a nice handle for the loop, right, doesn't mean that's a good strong handle that you can get extra pressure on. We still do not want to be using any more than 25 pounds of tension on that. After pulling the cable, you want to make sure that your cable is always going to be supported, whether it be in a J-hook, a hanger, or a cable tray. Cable trays are neat and used for protected installation. When we're going from closet to closet, once again, check out your path. Typically, closet to closet are going to be just one simple backbone cable going from point to point. When you're doing conduit pulls, okay, you want to typically when we're sending our cable through a conduit, you want to put a protector on the end of the conduit because in many cases the end of the conduit pipe is burred and abrasive and can tear your cable. And if need be, use a lubricant on the cable so that it slides through the cable much easier. Make sure that your conduit is open up on each end. Examine the ends for roughness. If need be, put tape on the end or a plastic protector. Attach send a string down through the line, attach your string, and give it a pull. For riser installation, okay, a lot of closets and equipment rooms will be on different floors. For short runs, the cable can be supported from the top with a mesh grip or similar hardware available from cabling hardware vendors. For longer runs, special cables may be used. A steel cable, which is called a messenger, which the cable can be attached, is installed with the anchors at the top or bottom, and then we can pull our cables that way. Although we call it a riser pull, it is much easier to lower the cable down than it is to pull. It is recommended so that we don't end up with too much tension on our cable. Okay. For our closets and our equipment room, okay, first and foremost, try to keep everything as neat as possible. If this is a new installation, remember that others will be inspecting your work and later will be doing moves and changes. Run cables neatly and carefully. Avoid sharp bends because they will hinder your cable performance. And if you have any excess cable, coil them up and out of the way and tie them loosely. Mark everything and document where everything goes. Okay. As you can see here in the figure on the left, you can see the pipes coming up, the riser pipes coming up through the floor. And you'll notice that the compound going around the pipes, that is called fire stop. Fire stop is needed on pretty much every building, and it's what it's needed for building codes. Figure on the right demonstrate after many moves and changes, even the nearest patch panel could end up looking like a nightmare. So it is important that we work to keep our rooms very neat. Okay, patch panels are mostly rack mounted. Cables must be brought into the racks and then terminated and then dressed neatly. Patch cords will be used by the equipment installers to attach communications hardware to each location on your patch cables. Okay, so in summary, both signal and signal quality are affected by installation, the installation quality. Cables must be the type and length specified and similar. Even too much pulling tension on a cable can ruin its performance because you might end up, excuse me, if you have 16 twists per inch, when you're done pulling too tightly, you might end up with 8 twists per inch, which will degrade the performance of the cable. That's just an example. Wireless networks are improving drastically and dramatically, but are vulnerable to security breaches if not carefully protected. It is also important to remember that wireless networks still need a cable run to the wireless access point. Network cabling must be installed according to the National Electrical Code, the NEC, including the requirement that it be done in a